the top of my head. I might have to flip over my notes here and there, but we'll see what happens. So my name is Paul DeWise. I own DeWise Engineering and Forerunner 3D Printing, and this presentation is that today is designed for 3D printing. All killer, no filler. What does that mean? I'm going to try and get right to the good stuff and get you into some information that's actually usable for designers and engineers. Now a little filler. I started DeWise Engineering out of my dorm room up at Ferris in 2009. My first CAD package was CATIA V5. This user group was a big part of me actually getting started. From 2009 to 2016, myself and my team built up DE. We do a lot of things in, obviously automotive, specifically shop floor automation and shop floor manufacturing aids, everything from hand tools to robotic assembly equipment, kind of everything in between. Do some aerospace work, a lot of foundry work, a lot of heavy agricultural, mining and construction. Then we also get into point of sale, point of purchase, and like fixture development. Like if you go into a Speedway gas station, you see all the tobacco vending behind there. That's a lot of stuff that we worked on for one of our customers. New product development, everything from working on literally right now we've got a customer that wants us to look at like making a recycling machine for cans to Taylor's done bathtub sized kayaks for American Girl dolls and everything in between. We very, very diversified kind of portfolio of work. And during that time, I used Select Manufacturing in Muskegon as my 3D printing vendor. Ross Gates was the gentleman who owned it. Me and him became friends. He didn't really have a succession plan, so one day in May of 2016, I get a phone call from Ross, and he's like, I'm done, I'm selling it, do you want it? I was like, your 3D printing business? He's like, yep. I'm like, I guess, I don't know, let's talk. So, got together, fair deal, fair terms, bought the business from him, really bought the assets from him essentially, and we formed Forerunner 3D Printing. So we started out with two SLAs, SLA 500, SLA 5000, running Next and Watershed materials. And then we diversified into POLOYJET 3D printing, and then literally 2 weeks ago we installed a HP MJF machine. And I'll get into machine specifics here in a minute. So that's a little bit about us. So the big thing is like, okay, design for 3D print. Well, I thought 3D printing was just unlimited Wild West, whatever I want I can get. Well, it is in most regards, but it's like anything. If you are designing a part specifically for injection molding or specifically for stamping or specifically for production machining, you can gain certain economies in lead time and in part cost and in tooling cost. Well, with 3D printing, you can gain those same things. If you optimize your design for 3D printing, you can get isotropically stronger parts. So instead of just traditional 3D printing where it's strong in the X and the Y, but the Z orientation, there's the layers, so you might have cracks form in that orientation under heavy load. You can get around that if you design properly. You can cut a ton of post-processing time. So, if you are taking and getting a part, and we'll get into this a little bit more, if you can mitigate the amount of supports that are required for it, you just cut all that sanding time. And honestly, next to material cost, human labor is one of the biggest cost drivers for 3D printed parts. So anytime that you can eliminate time on the bench is just putting money back into your pocket. And so there's some very simple things you can do to save yourself quite a bit on that. You can get added functionality and unique features. So 3D printing can do wild stuff that no other manufacturing process can really do economically. So you can design in features that can save you money and get you added functionality because this is a different kind of process. And biggest thing is you can lower your cost. A big part of what we do at Forerunner every day is working with customers to say, how can I take this from a $2,000 part down to a $1,000 part? And sometimes it's as simple as, hey, can you split the part here and we can put it together afterwards? Or, can we build it in a different orientation? There's always simple things that can be done that really don't affect the end part at all, but can save you a considerable amount of money. So the following examples are parts that we either design specifically for the 3D printing process or parts that we help customers redesign for the 3D printing process. One kind of fun one I threw on here. This is actually a steering wheel for a mafia-themed classic car. And so the guy found found a model of a Thompson submachine gun and had us essentially design him a steering wheel and then combine all the bodies and print it, and then he finished it in a body shop, and it looks pretty cool. So that's kind of a weirder one, but we'll get into some more practical stuff. So I'm going to quickly go through each technology, just so I can make sure that everyone's on the same page. I'm sure some of you know how this stuff works, some of you probably don't. I'm just going to hit it all, just so we're always on the same page. So we're going to start with SLA. SLA is a liquid process. It's like a two-part epoxy. Your A part is liquid in the vat. The B part is actually a UV laser. So when the laser comes down and it hits the top layer of the resin, it flash hardens it using that UV light, and essentially it just hardens layer after layer, and that platform just keeps dropping. And every time that platform drops, then you build your next layer on top of the layer underneath it, or the support underneath it. So that kind of bird nest material is actually support. So obviously you can't just build in thin air or in the middle of the vat. You have to build support up to hold your part. So that's kind of a quick run through of SLA. So first example is this guy right here, and I'll start passing these around. So this is a blowback nest, as we kind of come to call it. Essentially, the design challenge was to design a block that could route both high pressure air for blow off and strong vacuum to remove dust out of one part. We run a continuous feed of material across this. It has a powder coat going onto it, but they want to make sure that the powder isn't on one side of the part where they put it on the other side. So this block essentially routes high pressure air to blow off the bottom and then vacuum away all that dust and leave the top of the part untouched, so then it can go through the oven and actually cook the powder coat on. So we did some CFD analysis to kind of guide us on where to put the holes and how to orient them for the HPA blow-off and also for the vacuum. And it just turned into this real nightmare of like, okay, so we got to find an EDM hole driller, and it's got to be able to do at least 4th axis moves. And eventually what we kind of came to is, you know, what if we print this in a watershed and then we just put it into a stainless steel block, essentially, and the block will take any wear, but the watershed will allow us to route air and vacuum wherever we wanted it. And we tried it, and it actually works like ridiculously well. So there's multiple of these in use on a shop floor here in Western Michigan, and it's working quite successful for the customer. So get into the kind of talking about specifics here a little bit. So the purple that you see traced through the block is high pressure air. We're just running shop air at about 90 psi. Kind of the sea green, that is vacuum. And so essentially, if you look in this cutaway right here, you can see there's all these holes arrayed across the bottom of that. And essentially, they start from straight up and down the middle, and then they just kind of spread out in an arc. You can imagine trying to put all those holes in there with an EDM drill was going to be pretty complicated. And actually, it turned out to be non-manufacturable when we really got into it. But 3D printing really didn't have a problem with it. And then you can see there's these chambers right here. There's 4 of those chambers kind of spread through the block. Those are vacuum. And with those, we wanted to come to a very specific mouth size opening to get the right amount of draw, to get that dust to break loose and then suck in and not just be aerated into the atmosphere. So with 3D printing, you don't have to worry about, if we try to do this out of a traditional CNC type application, you'd probably end up having to bolt this block together from a bunch of different blocks and get seals and everything like that in there, because there's no way cross-drilling through a block would be able to create all the channels and everything like that that we needed in there to move air and vacuum around. So the one thing to keep in mind with 3D printing, if you're going to have trapped volumes like this, is support. So remember how I said with SLA, there's that bird nest type material that supports everything. Well, you got to eliminate that because it's inside your part. You can't get it out, and it's going to impede your airflow or your vacuum flow. So, the rule of thumb is a 45 angle is self-supporting in most 3D printing applications. In this case, you can see the roof of the vacuum chambers right there. Actually set those closer to like 60, just to make sure we really had plenty of angle and it should be very self-supporting. So there was no build, there was no support in either of those build chambers. And then an arch. So, one of the most basic, Roman era engineering principles, right? An arch is self-supporting when you get it all built together. Well, same thing applies in 3D printing. There's no support needed for this arch. And same thing with this round hole down here. There's no support needed in there. So everything is either a round, or is either a perfect circle, is an arch, or has a higher than 45-degree angle on it, so that we were completely support-free on the inside. And so yeah, so it worked really well for our customer, and this is just kind of like a quick example of one of the things you can do. If you design for the 3D printing process, you can do some really wild stuff like this. And I've also seen people do stuff like this with fluid too. People do a lot of stuff with moving coolant around or anything non-abrasive. If you get any abrasives in there, it's just going to chew this thing apart. But if you have a non-abrasive fluid, and also not high heat either, SLA isn't really good at high heat, so you want to try and run room temperature if you can. That's why air and vacuum are really great for this application. So if you've got questions as I'm going, just interrupt me, raise your hand, anything like that, and we'll just kind of keep moving through these quickly. So it's our first application. So that's SLA. SLA is predominantly prototyping. That's what we do mostly with our SLA machines. Shop floor applications are kind of few and far between, just because of it doesn't like heat. It's not the strongest in the world. It's a little bit, definitely more to the expensive side. So SLA doesn't have as many shop floor uses, but that is one of them. MJF. This is brand new. This is from HP. This machine's been out commercially about 2 years now. So like I said, we've been running these parts for about a year, and we just got our machine here a little bit earlier. So this is a nylon process. That's these parts here, this part here. Essentially, it's the machine lays down a 3/1000th layer of nylon, then it comes across and it sprays the black fusing agent, and then it sprays a clear detailing agent in the same pass around the outside. And it's a high temp internal environment, so the powder is probably within 25 degrees of its fusing temperature. So when that black fusing agent goes on there, and then a big powerful light goes over the top of it, it fuses that layer of nylon, but only where you apply the fusing agent. The detailing agent's there just to give you nice crisp edges and corners. So I'm going to pass around a whole handful of different parts here. You guys play with, and kind of go from there. And I got tons of other stuff up here too. If these don't make it to you, you come up and see me after the presentation. So there's a handful of stuff. All right, so MJF. So this is a sintered nylon process. These parts are 99.5% dense, airtight, watertight, pretty much equivalent in performance to machine billet nylon. It's very isotropically strong, X, Y, and Z, because of the fusing process that they use. So we see a lot of applications for this in like our engineering business, a lot of machine builds, so end of arm grippers and hand tools, nesting details. We've been working on all of those for some customers and having some good success. So this first one is a safety cover for a high-speed ratchet. So the customer was getting these machined out of Delrin, and they just kind of ran into this situation of lead time on the CNC every time. And because it's ratchets, they change constantly. There's not enough volume to justify a mold because they're constantly changing what ratchet they put it on, so they'd have to have a warehouse full of molds to cover every possible ratchet size, inch and metric that they might need. So they've been machining them, but lead times are getting longer and longer. The spindle, in this case, the lathe time is getting more and more expensive. And so they came to us and said, hey, is this something that we could maybe 3D print? And with this MJF process, I mean, we can fit 400 of these in one build chamber, so we agreed to it. But the problem we ran into is this is the original design that you see right here. It's a complete circle. There's no splits or anything like that in it. So when we went to assemble them, the nylon would actually just shatter because it's not quite as elastic as the Delrin is. So we kind of played around with it for a little while, and we realized, hey, if we put some pedals, some cuts into these parts and kind of pedal them, that allows the MJF part to just flex and then snap right back. And still has the same performance characteristics, holds on there really nice, but the parts don't just shatter when you go to assemble them. And that's one of the things to keep in mind when designing for like an MJF or an SLS type process. Your materials aren't going to be maybe quite as elastic as maybe like a Delrin or a UHMW. So trick is, pedal them where you can and give yourself, essentially turn these into 4 individual snaps instead of just one solid ring. And we found that worked really, really well for this and some other applications. Another thing that's really cool about 3D printing is labeling. So you can label an injection mold, you can stamp labels in, you can engrave labels on a CNC machine, but here it doesn't drive cost. I mean, it's literally you say, oh, can you throw this into the part or that into the part? No problem. It's 3 clicks and magics, and I've got whatever label I need in there. So customer really liked that too. We started printing the size into every single part, and they really liked that for when the guys are going to assembling, because inevitably a guy grabs a handful, they dumps them on the table, and then it's like, oh shoot, which one's which? So just printing the label in there was a big deal for helping them on the shop floor. So that's another example of taking a traditional machine part and transitioning it over to 3D printing. End of arm gripper fingers. So there's one of them going around right now, and I've got a couple others up here. These are really, really pretty cool. The issue that our customer was running into is they had really, really tight space that they had to load parts into an injection mold for overload, so inserts. And due to the number of grippers required, the end of arm tool also had a weight issue. Their robot didn't have the capacity to do a whole bunch of aluminum gripper fingers. So they were looking at machining them out of nylon, and that was going to work. But the only other thing was it was such a tight fit, and they had to have suction cups in the ends of here. There wasn't a lot of room to actually channel the air line around the outside of the gripper finger. So we kind of said, well, heck, I wonder if we could print the airline inside the gripper finger. And so the one going around, you'll see there's a suction cup inside, and there's a fitting on the outside. There's actually a 3D printed air channel through the inside of the gripper finger. So now when it reaches into that really tight space, you don't have to worry about an airline getting caught on anything. The airline is actually coming out outside of where it's reaching into the mold. So this is kind of a cutaway of what I was just talking about. And this, the fingers that are going around, it's, like I said, it's centered nylon. It's actually, and this is where my notes would be helpful, but off the top of my head, I think the aluminum version of this, we turned this aluminum in SolidWorks, and it was like 0.45 pounds. I'm gonna look real quick. 0.41 pounds, and the MJF version was 0.18 pounds. So there's a pretty significant weight savings with going with nylon. Nylon's good up to, I believe this is good up to 300 degrees Fahrenheit, so we didn't have an issue of, these getting all floppy on us in the mold if it's getting ambient heat put into it every time it reaches in there. And that printed air channel worked out really, really slick for moving the air through there. And then if you look at this as you go around, I mean, if you wanted to do this, this could be simplified a little bit, but if you want to do this on a CNC machine, you'd be like probably, I think 3 setups to do this, and then you'd have to be gun drilling into it to put your internal air line through it, and then you've got to put your plugs in. So it can be done, definitely could be done traditionally on a CNC machine, but I can print this out the door with the fittings into it and sell it for $100 a piece. So the part that's going around with fittings in it, that's $100 out the door. In this material you can drill and tap it. So in this case we ran pipe taps into it, put our fittings in there from EMI, and I mean it holds vacuum, works really, really nice. We have, I haven't done it yet, but one of our vendor who installed this machine for us, they're over in Detroit, and they've been doing a lot of experimenting. They've run these up to 125 PSI and haven't had any issues, so it's pretty stout stuff. Obviously, if you make it small enough, eventually it will burst, but if you make a beefy part, it'll hold up to some pretty good pressures. So, end of arm gripper fingers. Oh, and the last thing, there's a texture that we put in here to help grab onto the parts. In this case, the only way you could do that in traditional manufacturing would be like an EDM sinker type operation. And again, you can print your textures right in. I was just at IMTS yesterday and went through the HP booth, and they have customers from all over the world that they grab sample parts and bring them in. And some of the printed in texturing that people are doing for decorative is just wild. If you've got some time, check out the HP website. I know they have some sample parts up there with these printed in textures that is just like crazy looking. So that's our gripper finger example. Another interesting one, and this is one we're still like literally in development on. One of my buddies is a photographer, and he also has a Amazon operation that he runs, sells a lot of custom-made camera gear on there. And he came to me when I got this machine, and he said, hey, I would love to do customized lens caps for people. So essentially I can put your name, I can put your logo, whatever you want into your lens cap. And he said, but I got to keep it $35 on my Amazon page to be able to really make these things sell. Is that something that you can do? I'm like, I don't know, let's try it. So we did. This is one of our 1.0 versions, so I'm not going to pass it around because it's all broken and not really that great. But I'm going to show you what we did to fix it. This is really neat because when we're talking about trying to hit that $35 price point, I really need to be able to sell it to him for 10. And he's going to order them 100 at a time, so we've got the quantity that we need. And to customize it with different names and stuff like that. Again, it's 10 seconds a piece in Magics, and we have an intern whose life all ruined with that job, so it's not like a big deal for me. So the trick was though, he's like, well, the one he gave me to model, it was a 3-piece design, and it had 2 springs that they put in there to get that spring action, so it would lock into the end of the lens. And I'm sitting there going like, man, if I gotta buy springs, and I gotta put together a little assembly station, and then I gotta pay someone to sit there and assemble these things, and it's gonna start to add up. So we've seen other people do it, so we thought, hey, let's try 3D printing this as a complete assembly with the springs built in as printed features. So this nylon, HP does have a glass-filled version of PA12, which is this material, this nylon. We are not running the glass-filled version right now. We're just running straight PA12. So these, you could try the one you got out there. You're not bending this. This is very stout. But if you keep the form factor thin enough, it is pretty springy. And so what we did is we experimented, and you can see this gap right around here that is all the way around the part. We found 0.2 millimeters. If you leave a 0.2 millimeter gap to 0.3 millimeter gap around your assembled components, they'll print, they won't fuse together, and then you can break the powder out just by actuating them a little bit. One of the reasons this is broken is you'll notice this area is solid, and up there, that area is open. We didn't think about, hey, the powder's got to get out of this after we print it. So we printed it, and then I went like that, and it just went crack. I was like, oh, well, that didn't really work. All right, spin us another one. And that's the other cool thing about, prototype production is kind of what some people are calling it. You print 3-4 different designs with your springs, because you can take a spring design that you traditionally use in injection molding. That's a really good starting spot for 3D printing. But then you can kind of tweak it from there, and it's all about iterating these springs, right? Well, the nice thing is you throw 4 of these in the machine, you print them overnight, you come in, okay, that one didn't work, that one didn't work, that one didn't work. Oh, this one worked pretty good. Iterate on that 2 or 3 more times, and then, literally next week, we're going to do our first production run of 100 of these, and we're able to sell them out the door to the customer for $10 a piece, and he can go and retail them for $35 on Amazon. So you can print assemblies, you can print springs into your assemblies. Like I said, beating a dead horse. I was at IMTS yesterday, and some of the stuff I saw people doing at the EOS booth, which is an SLS machine, kind of similar to this. HP booth, there's guys printing full gear drives and assemblies, totally enclosed. They put them into a parts washer, wash all the powder out, and go. I mean, they're doing gearboxes out of this stuff with, you know, very minimal openings, just enough to get the powder out, and then they plug them. So, you know, really, like, you know, I hate to sound, you know, all full of hyperbole, but like, if you can think of it, like, there's a good chance you can actually get it to work with MJF or SLS technology. So, kind of a neat application. So now we're moving into FDM. This is like kind of the mainstay. This is the MakerBot. This is the MarkForge. You've got your spools of material. You feed them through, and you've got a support material and a build material. And you know, these machines, you know, are really, really good. In our business, we have one, and we always kind of use it for a lot of hand tools and a lot of more of kind of the quick and dirty models, you know, to kind of get up and running. So here are some hand tools that I'll get into in a minute. Best thing about this is it's cheap. You know, I can go on Amazon and buy a roll of material for $27. And so, you know, my customers, they need hand tools, they need a lot of them. They don't want to spend, you know, $1,000 a tool. They want to spend $100, $50 a tool. And that's what we really like this for, is it gives us the ability to iterate really easily on hand tools and then to make them at scale for a reasonable cost. So first application here is a tape hand applicator. So the challenge, design and 3D print a series of ABS plastic hand tools that can be used to guide the application of tape onto windows during assembly. Our customer supplies all the tape to Anderson Windows down in Mexico, and these factories are just full of people, and they tape all the windows together. There's not a screw or a bolt in any of those windows. It's all double-sided sticky tape. You go look at a skyscraper, that's the really crazy part, because I'm like, oh, Anderson Windows, okay. And then he's like, yeah, well, next time you go downtown Grand Rapids, look at the Marriott or look at the Amway Grand. All that glass is held in with double-sided sticky tape. That's it. Now, this double-sided sticky tape, I also know for a fact, if you make the mistake of setting a roll of it on its side on your desk and going home for the weekend and coming in, you're going to peel all the laminate off your desk to get that roll off. So it's very, very high-end tape, but still, it's just tape, kind of crazy. So the tools were going to be used on a daily basis, so they needed to be robust, they needed to be able to stand up to wear and tear. And then there's a large range of window sizes and designs. That, coupled with the cost to set up CNC machines for each size tool required, and the need to, for the finished cost of the tool to be less than $100 each, made traditional machining too expensive. They had been machining these out of Delrin, and it's actually this style is what they were machining out of Delrin, which didn't have the rollers in it or anything like that. And they could, because of the variety of sizes that they needed and the fact that they only needed 10 to 12 of each size, they could never get the cost really low enough to make it super competitive. Because at the end of the day, the tape company gives these applicators a way to help sell more tape. So they want to make their customers as happy as they can, but they don't want to pay anything for it. So it's kind of one of those catch-22 situations. So we got involved, and we kind of said, okay, let's look at this and see if FDM printing would be a way for us to do this where it's cheap enough to get the price point that you want, but flexible enough to cover a wide range of sizes, and it's low enough volume where you don't have to buy 200 of them to hit the prices that you want. So what we came up with is, and then once, it's kind of like most things, once we sat down with the customer, talking about the flexibility that 3D printing provided, he started thinking, he's like, well, what if we put rollers in? Because, you know, after they take and they put the tape down, then they got to take a little roller and sit there and go across it and wet the tape out. He's like, could we combine the roller with the tape applicator and save them a whole set of movements? And so we're like, I don't know, let's try it. And that's what we did. We tried it, and it worked like gangbusters. Like, they sent one down to Mexico, and like a week later they got an email back, and they're like, everything needs to be like this. Don't ever send us one of the old ones again. Which is great. Our customer's happy, his customer's happy. So then the next challenge kind of became, okay, you know, let's figure out how to kind of, you know, make it robust, a design that's robust enough. So One of the things you'll notice on these blue ones is the sides are flat, and they have a different finish than what you see on the rest of it. The rest of it has that kind of traditional, layered feel to it. Those sides are flat. And that's because when we designed this, we said we want to design this with as little support material as possible, because remember, support material just drives time, and time drives cost. So we're trying to keep the cost down. So we designed these to be printed as you see in this picture right here. Lay them flat on the bed, print everything up. And literally the only support we have to break out is in these counter bores here, and in these counter bores over here. We have to dig the support out of there, but that's not too bad. 2 minutes with a screwdriver, that's all cleaned out. Go in there with a Dremel, sand in a quick second, and you're done. So 3 minutes per part for D, kind of benching them, that's inconsequential to the cost of the part. Another thing we did with this is when we print them straight up and down, and this is kind of across the board for all 3D printing. If you need a truly round part, or a round part or a round hole, or you have dowel holes, and you need them round and locationally accurate to each other, you always want to orient your part vertical in the Z-axis. You want that hole facing up. That gives you the best chance of not having to dig support out of the hole. And also, if you build that hole on its side, it's not really round. It's more kind of egg-shaped when it's all said and done, because of how the layering works and how the part kind of settles as it prints. So your best bet is to flip it straight up. And so that's another thing we did, is we had all of our holes pointing straight up into Z, so they were nice, true, round holes, and we didn't have to worry about them being egg-shaped, because we have this roller. We've got that kind of bluish roller in there. We want that to run nice and smooth. And we found when we stood them up, the inside would be rough, and it would just kind of hiccup and get really messy when it rotated. It didn't do a really good job. We put them on a side, rotates really nice. We had bearings in it originally. We wanted to pull those out and just running it right on the 3D printed part because it was smooth enough. Another thing to think about in orientation is with FDM, if you have an angled surface like this up in the Z, and you're printing up like this, you get a stair-step effect in that. So you can see we have these ramps on here. We wanted those ramps to be super smooth all the way up where the tape was feeding through. So by laying it on its side, and all of a sudden your printer is tracing that ramp. So there's no stair stepping, it's a true smooth angled ramp the whole way. And so that was another thing that we found that made a huge difference in the kind of quality of these was doing that. So kind of key takeaways, make your holes facing up wherever possible. Kind of think about how your layers are going to be oriented and how your part's going to be used. You kind of optimize things that way. And then also, last point on these, they need to be strong. So we printed these at like 85% dense. So there's a lot of density to these parts. Typically if you go and get parts FDM printed, they'll run them around 13% to maybe 25% infill, and those are they feel real good. They'll work good as models, but if you start using this hand tools, they can start to break down on you. So you want to get that density up. This is a weird one. Dog head MRI fixture. So in my career, I've had some really weird phone calls of people asking me to do some really weird things. This was by far one of the weirdest. We got a phone call from a lab in Muskegon, and they were like, "Hey, you're in that 3D printing business. We need a fixture." And we're like, "What do you need a fixture for?" They're like, "Dogs and MRI machines. We need to, when we sedate them, we need to lock their heads into position so that they don't," because I guess when dogs are sedated, they kind of like your dog at home, like the leg just starts kicking for no apparent reason when it's knocked out. Well, the same thing happens when you sedate them. So the dogs in the MRI machine kind of moving all over the place, and that doesn't work real well for an MRI. So they want to sedate them and then fixture them into position so that they can take good, clean MRI images, and that's that. This is not our lab. This is just a goofy picture I found online to prove that, yes, dogs. What's really crazy? When I typed in animal MRI, racehorses. Holy smokes, there are custom-built MRI machines just for x-raying the knees and ankles of racehorses. So on your lunch break today, Google racehorse MRI and be amazed. So yeah, so the fixture needed to be very flexible too, because dogs come in many shapes and sizes, so it's not a one size fits all. So it looks a little medieval, but I promise no dogs were harmed with these fixtures. They're trying to help the dogs. So they use these two to kind of position off of the dog's ears, and then these two flip into its jaws. And one of the things that was interesting is those targets are actually they're loaded with mineral oil, because mineral oil glows super bright in an MRI, and they use that to align various shots off the MRI machine, and then some software they're using. They had to have these glowing targets. So, and again, they were very adamant on the positional accuracy of these cylinders in these 4 different areas need to be as accurate as possible. So we actually built these standing straight up on the bed of the FDM machine. They were about that tall, but you know, you've got a perfectly round cylinder in the center of that part. We just pour mineral oil in there, and then cap the end of it, and then you've got your mineral oil target. So again, orientation was really important on those two. You know, build strength was really important too. So like the frame here around the outside, the kind of horseshoes on the bottom, and then this back piece and those blocks, we actually printed those at 100% density. So they're as dense as we can get an FDM part, and that just makes them insanely strong. So again, when you're talking FDM, be thinking about your strength requirements, and let your, you know, either your internal guy or the service bureau you're working with, let them know, like, hey, I really need it strong in this orientation, I really need it strong for these types of loads, and there's things we can do to improve the strength of your parts. But also the flip side is true, if it's not a real load-bearing part, let us know that too, because we can drop density, and that'll save you time and money. If we can make the parts with a 13% infill, that's going to cut our build time down by, I mean, on something like this, you could literally shave 40, 50 hours off of build time just by dropping your density from 99% down to 25%. Another thing is, so it's an MRI, can't have any metal in an MRI. That's why we originally got the call. But, you know, one of the things is you see these green fasteners all over the place. Well, we still had to be able to adjust the thing, so we needed stuff to be threaded together, but we couldn't. Typically, when we 3D print parts, we'll helicoil the holes. Like if you're going to be bolting something into a machine, you might be taking those in and out, in and out, in and out. We'll helicoil, or we'll epoxy insert with brass threaded inserts into the part to make sure that those threads don't just burn out. Well, we can't helicoil this, so what we came up with is, okay, we're going to, you know, first off, if you're going to use, you know, actual tap threads, try not to go below 1/4 20. Obviously, I violate that rule on this one here, but this is like a one-time assembly. Like, you probably aren't going to be pulling this thing apart and putting it back together a whole bunch of times. But if you are going to 3D print threads and you are going to be taking it apart and putting it back together quite a bit, don't go below 1/4 20, and half is even better. If you can get it to the 1/2 inch size range, those are really, really good when you tap them in 3D printing. You can 3D print threads too, but that gets really, really tricky, and it's a big cost driver. So we always like to say, like, if we can just, you know, drill and tap afterwards, we prefer to do that. You know, we'll, you know, like if we're using, I probably should use this as an example. Some of the CATIA users, if you're using SolidWorks and you're in the hole wizard, you know, you can literally tell it, you know, hey, make this hole the tap drill size. And then all you gotta do is really take a tap, spin it in there, and you're done. But in this case, we kind of had an epiphany and said, hey, if we're gonna tap into the FDM plastic, let's actually buy plastic screws to go with it, because obviously we can't have metal, but plastic thread on plastic thread is gonna last a lot longer than metal thread on plastic thread. So even in you guys' applications, if you are going to be tapping these parts and putting them together, if you can get away with using like nylon screws off McMaster, you know, try and go that route, because your threads are going to last a lot longer that way. So, you know, kind of the takeaway from there, helicoil or insert if you can. If you can't, drill and tap, don't print the threads, and then try and use plastic fasteners. So yeah, so that's my presentation. I came in 5 minutes under what I wanted to, which is great. Are there any questions? Anything you guys want to see more of? Okay, perfect. Well then, thank you so much. Oh.
When you acquired the 3D printing business, did you move all the equipment then to your,
Yeah.
your Cooper's, right?
Yes, oh man, yes we did. Yep, there was the building was in rough shape, and the room that the machines were in was even rougher shape, so yeah, we just acquired the assets, moved them to Coopersville, and then literally rebuilt them. The first thing we did was strip them down to pretty much the frames and put new lasers, new computers, new mirror drivers, everything. Pretty much the only thing left original on those machines is the sheet metal enclosures that they're inside of, and then some of the drive mechanics for moving the backs up and down. So, yeah.
The low-rider steering wheel.
Yes.
Did he break it yet?
No. You know why I didn't break it yet?
Well, that's what I was going to ask you to talk
Because
about.
I told him, don't drive it. What I told him is, he said, well, I want to drive with it. And I said, then I'm not going to print it for you, because the last thing I need is getting a call from the state police that says, well, some dude was driving down the road and his steering wheel just snapped in his hands and he just wiped out a school
He was
bus.
impaled by a machine gun.
Exactly. So what
Design
we,
considerations, what did you make for changes on that to make it actually work?
he literally found full models of Thompson submachine guns online. Like if you wanted to machine a Thompson, he had the model for that, which is great, except I don't want to 3D print 300 pieces and put it all together. So what we did is we went through and densified the entire thing. So again, good job for the intern. I handed him that Thompson model and I said, when I'm done, I want to come back and I want to see a single body in the tree. I don't want to see 600 bodies go. And so we did that. There was definitely some parts in there that we couldn't print in the orientation that we were going to print the gun, so we split those off. And then we actually assembled them back on and welded them in place light welded them with epoxy in place once we were done. But what we ended up doing is he put one of those like racing quick change adapters behind it. So what he would do is when he got to the car show, he would pull off his street steering wheel and quick change this steering wheel onto it. And that was kind of the compromise that we came to, so that he could get his steering wheel and I didn't get sued.
Right.